Welcome back to Carneades.org. Today we're going to be continuing with our series, Dumbfounding Definitions, Dizzying Distinctions, and Diabolical Doctrines, a series sorting through some of the jargon of philosophy. Continuing with our theme of A Month of Saul Kripke, we're going to be looking at what is Kripke Semantics. This is going to be a bit of a more difficult video, at least in terms of logic, so if you don't have a background in logic, I would check out the 100 Days of Logic before watching. So, there are a range of different types of modal logics, which all use a similar set of logical axioms and rules to govern them. They focus on a diverse range of topics from time, temporal logic, to ethics, deontic logic, to knowledge, epistemic logic, all the way, of course, to alethic modal logic, the traditional thing that we think of when we think of modal logic. However, similar rules are used to govern each one. In our series, 3 months of modal logics, we delved into the axioms for each of these systems and touched on the semantics that provide meaning for these axioms, but we focused a lot more on syntax than semantics in a lot of those. In this video, we will go into depth into what's known as Kripke Semantics, which really underpins a lot of modal logic, and explain how it can be applied over all of the modal logics and how we can interpret our axioms using this system. You definitely don't need all of the 3 months of modal logics to understand this video, but checking out the video, particularly at the end of the 100 Days of Logic on the modal logic basics, would be advisable, and then maybe watching just a couple of the intro videos to each of those 3 months focusing on deontic, temporal, and epistemic might help out, but if you don't do that, you'll probably still have a good basis if you at least have some understanding of the modal logic basics. So, there are 3 important elements to Kripke semantics. Remembering, semantics more focus on meaning, while syntax more focuses on kind of the rules and structure of a language. There is the set of possible worlds, frequently represented with W. There is the accessibility relation between worlds, frequently represented with R. And there is the valuation operation, which holds between a proposition P and the possible world W. We will describe each of these elements, then describe how they interact with each other, and finally map them onto the axioms of the various modal logics. So, the set of possible worlds is frequently represented with W. In most modal logics, these represent other possible worlds. But for example, in temporal logic, they represent instants of time, or in branching temporal logic, they can represent branches of time, or if you're doing interval, they might represent intervals instead of instants. Anyway, individual possible worlds are labeled as W1, W2, W3, etc. Each world has a set of propositions which are true in it, and a set of propositions which are false in it. Sticking with classical logic for now. All of the atomic sentences in a world, sentences which have no logical operators in them, remembering logical operators are things like conjunction, implication, but also things like for all or there exists, are given a truth value. This assignment is known as a valuation. Truth values of sentences with logical operators are determined by truth tables. So what that means is you take those atomic sentences that are true or false, and then you plug them into a truth table to decide whether that larger statement, P or Q, P and Q, is true. Valuations are represented with usually a lowercase v or that symbol there. However, we're going to use a capital V to represent valuation to prevent confusion between this and disjunction. They're written as VPW, where P is a proposition and W is a world. These valuations would output a truth value. So, in the example to the right, the valuation of P world 1 and the valuation of U world 2 would be true, because we note that P is true in world 1 and U is true in world 2, though P is not true in all possible worlds and U is not true in all possible worlds. However, those 2 valuations would be true because they're specifying the proposition and the world. But the valuation of Q in world 1 or the valuation of Q in world 3 would be false, because we note that Q is false in world 1 and Q is false in world 3, even though Q is true in world 2. Going further, the valuation of P and Q in world 2 would be true, because both P is true and Q is true in world 2. And using our truth table, we can find out that in order for a conjunction to be true, both the conjuncts need to be true, while the valuation of U implies P in world 3 would be false, because for an implication to be false, the antecedent needs to be true and the consequent needs to be false. So hopefully that gives you a sense of valuation and the way it works. Basically, we're just taking our basic ideas of truth tables and we're expanding them to not only are we isolating things by proposition, but also by world as well. The third part of Kripke semantics is the accessibility relation. This is a relation between worlds represented by R. It can be written as R, W1, W2, which means that W2 is accessible to W1, or W1 accesses W2. Note that those aren't interchangeable. W2 is accessible to W1, and W1 accesses W2 mean the same thing, but just because W2 is accessible to W1 doesn't mean it can go the other way around, and we'll talk about that later. This means that if a proposition is necessary in world 1, then it must be true in world 2. Or to state this another way and define this relation, for all propositions P and all worlds 1, the valuation of it's necessary that P in world 1 is true if and only if for all worlds 2, such that world 2 is accessible to world 1, then the valuation of P in world 2 equals true, where T represents true in that statement. So in other words, any world 2 is accessible to some world 1 if and only if for all propositions that are necessary in world 1, those propositions are necessary in any world 2. Hopefully that makes sense. Don't worry, we will give a lot of examples to be really clear on this. So it's important to remember that the strong modal operator can mean logically necessary, but these rules are going to also apply in other kinds of modal logics, because it can also mean morally obligatory. Will always happen in the future, and more, depending on the modal logic that you're using. If we're using deontic logic, the accessibility relation is usually replaced with something known as the acceptability relation. Basically, one world, world 2, is acceptable to another world, world 1, if and only if something is obligatory in world 1, then it is true in world 2. So, since obligatory is the strong modal operator in deontic logic, what we're saying is, instead of just having it's necessary that P in world 1 means that P is the case in world 2, saying it's obligatory that P in world 1, so you must do the most good for the most number of people in world 1, means that you always do the most good for the most people in world 2. It's actually true in some other world. Temporal logic takes this a step further, since their possible worlds are actually instants on a timeline, and we'll use the precedence relation, so that some instant I1 only precedes another instant I2 if for any statement P in I1, which will be the case for all instants after I1, that statement is true in I2. Hopefully that makes sense. For more on these relations, check out the specific series on deontic and temporal logic, respectively. We do a lot on the precedence relation in temporal logic, and in deontic logic, we do actually cover a little bit of these kind of modal logic semantics with Kripke, and we talk about the acceptability relation. All right, so let's take a look at a set of possible worlds and whether or not they're accessible to each other. So we have world 1, world 2, world 3, world 4, world 5, and world 6. In those worlds, they have a different set of propositions which are true in them, and a set of propositions which are necessary in those worlds. Note that because we don't have useful modal logic axioms like Axiom T yet, it's possible for a statement to be necessary in a world, but not true in a world. And also remembering with our different range of modal logics, it could be that box might not be representing kind of alethic modal necessity or logical necessity. It might be representing deontic necessity, and which is obligation. And so obligation, it might be obligatory that something is the case in the world, and it might not actually be the case in that world. But putting that aside, whatever those things are representing, they're representing the same things for all of these worlds in this diagram. So just take it as the strong modal operator. We'll refer to it as necessity, but think of it as the strong modal operator here, because it might get confusing otherwise. All right, so let's take a look at world 1 and see what worlds are accessible to world 1. So the first arrow that we have up here says that world 3 is accessible to world 1, or world 1 accesses world 3. So what does that mean? Well, that says that anything that's necessary in world 1 is true in world 3. So it's necessary that P and it's necessary that Q in world 1. We go over, we look at world 3, we say P is the case, Q is the case. Great. Now, is it accessible the other way around? I don't think so. Let's look. That would mean that all of the things that are necessary in world 3 have to be true in world 1. And in world 3, we have it's necessary that R and it's necessary that Q. And we have Q in world 1, but we have not R in world 1. So our accessibility relation is not going to go the other direction. While world 3 is accessible to world 1, or world 1 accesses world 3, it's not the case that world 1 is accessible to world 3. All right? Now let's take a look at world 1 and world 2's relation. Well, world 2 is accessible to world 1 because it's necessary that P and it's necessary that Q are the two necessary statements of world 1, and both P and Q are true in world 2. However, world 1 is also accessible to world 2. Why? Because the two necessary statements in world 2 are it's necessary that P and it's necessary that S, and both P and S are true in world 1. So our accessibility in this case goes both ways. Now let's take a look at world 4. So in this case, world 4 is not accessible to world 1 because world 1 has it's necessary that P and it's necessary that Q, and world 4 has both not P and not Q. However, the opposite does apply. So world 1 is accessible to world 4 because in world 4, the only necessary statement is it's necessary that not R. And in world 1, not R is the case. So world 1 is accessible to world 4, but world 4 is not accessible to world 1. All right. Hopefully, those relations make sense. And now now that we've looked kind of at what world 1 has going on, let's look at worlds 2 and 3. So world 2 is accessible to world 3 because the statements that are necessary in world 3, it's necessary that R and it's necessary that Q are both true in world 2. R and Q are both the case. However, it is not the other way around. It's necessary that P and it's necessary that S, but not S is the case in world 3. Now, some worlds are accessible to themselves. Take a look at world 1. It's necessary that P and it's necessary that Q are necessary statements. That's all the necessary statements in world 1. And both P and Q are true in world 1. So world 1 bears the accessibility relation to itself. World 3 also bears the accessibility relation to itself. It's necessary that R and it's necessary that Q, and both Q and R are true in world 3. And the same is true of world 4. World 4 bears the accessibility relation to itself. And so does world 5. We haven't really looked at world 5 yet because world 5 is not accessible to any of the other worlds, nor are any of the other worlds accessible to it. Look at the specific necessary statements in world 5 and the other worlds and the statements that are true in world 5 and the other worlds, and see if you can see for yourself why that is the case. So world 5 is accessible to itself because it's necessary that not S and it's necessary that not Q in world 5, and not Q and not S are true in world 5. However, it's interesting to note that world 6 not only is not accessible to any of the other worlds, nor are any of the other worlds accessible to it, but it is not even accessible to itself because it has it's necessary that Q and not Q in there. Like I said, check out those specific statements. Look, try to build more accessibility into this, but I'm pretty sure this is all the accessibility you're going to get. Now, taking a step back, this might seem confusing since frequently we think of necessity as logical necessity and claim that there are no possible worlds which would not be accessible to the actual world. Basically, the idea is that a world is only a possible world if anything that's logically true, necessary here, is true in that world. But the reason that this is confusing is because that's just how we're defining the set of the possible worlds that we're looking at. If we had a different understanding of possibility, or we were looking at all different worlds, maybe some of which had contradictory statements or broke the laws of logic, those worlds wouldn't technically be possible in our traditional sense. Why would they not be possible? Because they are not accessible to the actual world, because statements that are necessary, such as the denial of contradictions in the actual world, are not true in those other contradictory worlds. It's also important to think about this in terms of the other types of modal logics, such as temporal and deontic logic, remembering that clearly even a world being self-accessible isn't going to make sense for deontic logic. Or temporal logic, you might have all the moments after a certain moment bear the precedence relation to that moment, but not the moments before it. So deontic logic, branching temporal logic, and other things, there will be worlds which are not logically accessible by modal alethic logic. So these worlds bear different relations depending on which modal logic you're talking about. So depending on what we define that logical strong operator as, that modal strong operator as, will depend on which worlds are accessible, or as with deontic logic and temporal logic, we might define different relations such as acceptability or precedence. Okay? And it does seem strange to have worlds that are not self-accessible. So it seems strange to have things like world 6, where we have it's necessary that Q and not Q. But remember, until we get the axioms D and T, or those rules about the relation of accessibility, that's not guaranteed. Right? Take some time staring at that diagram. Hopefully it can provide you some insight into what we're talking about here. Along with the definition of accessibility, relation, and necessity, which we've already stated, we also need definitions of a couple of our logical operators. Specifically, negation and implication is what we're going to go with here, but you could pick negation and disjunction as well. They're very straightforward and follow directly from our truth table understandings of these concepts. Negations for all propositions P, all worlds, world 1. The valuation of not P in world 1 is true if and only if the valuation of P in world 1 is false. That's just the definition of negation. Implication for all P and all worlds 1. The valuation of P implies Q in world 1 is true if and only if the valuation of P in world 1 is false, or the valuation of Q in world 1 is true. Now, that we have a sense of how this semantic framework kind of functions, we're going to look at how this can map onto our modal logic axioms, our kind of syntactical rules that we talked about in Modal Logic Basics, but also throughout the 3 months of Modal Logics. The Modal Logic Basics video has a refresher on the axioms, or for a more advanced version, check out the Axioms of Modal Logic summary near the end of the 3 months of Modal Logic. I think it's the first video of the final 10 days of Modal Logics. We will just be looking at the semantic formulation of axioms K, D, T, 4, and 5 here. We're not going to get into any of the 4.1, 2, 3, 4, whatever that is, here. We're just going to be looking at K, D, T, 4, and 5. All right? So axiom K, named, interestingly enough, for Saul Kripke himself, which states it's necessary that P implies Q implies that it's necessary that P implies it's necessary that Q, is semantically simply the definition that we just offered of the accessibility relation. If P implies Q is necessary, then in all worlds accessible to this one, P implies Q is true. If P is necessary, then in all of those same worlds, P is true. And by our definition of implication, in all of those worlds, Q must be true. Therefore, by our original definition of accessibility, Q is necessary. So based on our definitions of implication and accessibility, we can prove axiom K. So this is just going to be a different representation of the axiom, the basic definition of accessibility that we stated before. Now, axiom D is going to go a step farther. It'll claim the following semantically. It's going to say that for all worlds 1, there exists some world 2 such that world 2 is accessible to world 1. Or in other words, for all worlds, there's at least one world which it accesses. Or one world where all the propositions under the strong operator in the first world are true. For something like deontic logic, this makes some sense, since it seems that anything which is obligatory should at least be permissible. Or in other words, for all worlds, world 1, such that there should be at least one world, world 2, which is acceptable to world 1. All the obligations of world 1 are fulfilled. All right? Or in other words, our obligations are not in some way impermissible or impossible to fulfill. This means that the relation is serial. Check out my videos on deontic logic for more if you didn't understand the example, but basically we're saying that this rule that there must be at least one world such that the accessibility relation applies is the same as saying that axiom D is the case, which makes sense. Saying that it's necessary that P implies it's possible that P means there has to be some world such that the accessibility relation will apply to it. So, world 6 would not pass this test from our previous example because world 6 there was no world which was accessible to it. Or rather, which it accessed. Either one. Axiom T, it's necessary that P implies P will be the following claim semantically. For all worlds W, world W is accessible to itself. Or in other words, all worlds bear the accessibility relation to themselves. This makes less sense in deontic logic since not all obligations are fulfilled in this world, but makes more sense in, say, epistemic logic, where for someone to know something in a particular world, it implies that that thing is true in that world. This means that the accessibility relation is reflexive, or all worlds are accessible to themselves. So a world like world 2 in the earlier example, which was not accessible to itself, would not pass this axiom. Axiom 4 is a little more complicated. It makes the following claim semantically for all worlds 1, 2, and 3, where world 2 is accessible to world 1, and world 3 is accessible to world 2. That implies that world 3 is accessible to world 1. Or in other words, if one world is accessible to another, and that world is accessible to a third, then the first world is accessible to the third. This makes the most sense in temporal logic, since if some statement D, say that the statement is Leonardo da Vinci is dead. If we say, at this moment right now, in our world, in our instant, that statement will be true at all moments in the future. So the strong operator will be true at all moments in the future applies to the statement D. Leonardo da Vinci is dead. Then it's not just the case that D is true at all moments in the future, but it's also the case that at all moments in the future, it is true that at all moments in the future, from that future moment, D will be true. Or in other words, if GD, D is true at all moments in the future, then it is true that at all moments in the future, it is true that all moments in the future, D is true. If Da Vinci will be dead for the rest of time, then at any future point, he won't just be dead, but he will still be dead for the rest of time. This means accessibility is transitive, or precedence in the case of temporal logic. And finally, axiom 5, which is it's possible that P implies it's necessary that it's possible that P, which is quite controversial, will be the following claim semantically that for all worlds 1, 2, and 3, if world 2 is accessible to world 1 and world 3 is accessible to world 1, then it implies that world 3 is accessible to world 2. Or in other words, if one world is accessible to two other worlds, then those worlds must be accessible to each other. This axiom is controversial in effectively all of the modal logics that we have examined. Basically, it is claiming that all of the worlds which are accessible to this one are accessible to each other. Watch the video on the basics of modal logic to understand why this is problematic. If this is the case, then accessibility relation is considered to be Euclidean. And it's an interesting note, axiom B, which we didn't cover here, but that's an axiom which leads to S5 when added to S4, makes accessibility symmetric. Or in other words, no accessibility relation can go only one way. They have to go both ways. So, those were the axioms, the semantics of modal logic, and Kripke Semantics. So that was what is Kripke Semantics. Next up, we're going to be looking at Kripke's theory of truth and continuing our series. Finally, you can't handle the truth. Then we'll look at Saul Kripke versus presuppositionalism, naming necessity, rigid designators in Saul Kripke, and of course a special Halloween surprise. Watch this video and more here at Carneades.org, and watch a video every single week for the month of October on Saul Kripke. Stay skeptical, everybody.